Okay, so we'll just keep going here with binary search. This was an example where we actually found our target value in position 5, but I want to walk through like if you don't find it. So basically, we got to think about like, I think this is a while loop. So we keep going while it still makes sense to guess, and then if we don't find it, we return -1, right? Basically representing we didn't find it at any one of our indexes. Okay, so an example here would be 10, right? So 10 isn't in this array, right? So I want to just walk through what this would look like, and then the exit condition that we would hit. Okay, so the idea here is, again, we have low, mid, high. So low starts off at 0 all the time, position 0 in the array. High starts off at length -1, and then mid is you add them together and divide by 2, which truncates in this case to 4. So we compare our target to this, and since our target is smaller, we can eliminate this one and all the ones above it. Okay, and the way we do that in the code is we have high become mid -1, right? So what happens is low is still 0, high is 1 less than what mid was before, so it's 3. Okay, and then mid we're going to recalculate by doing high plus low, 3 divided by 2, which is 1.5, which really means 1. So mid is now going to be down here. Mid is now 1. Okay, and so we check for our target, and our target is greater than this. So we can eliminate this one, anything below it, and the number itself. And we do that by jumping low to be 1 more than mid. Okay, so low is now position 2, high is still position 3. Okay, and then we recalculate mid. So mid would be 2 plus 3, 5 divided by 2, which would be 2.5, truncates to 2. So mid is now the same thing as low. Okay, and so we check here, right? We check our target for a target of 10, and 10 is bigger. Okay, so we can eliminate this one, and then we're going to jump low up here to be high, right? Above mid, 1 more than mid, I guess. I shouldn't say to be high, just 1 more than what mid was before, right? This is where mid was. So now we have low of 3, high of 3, and then we just go one more time, I think, where basically we want to check, because we got to check this spot yet. We haven't eliminated it yet. And so we do add them together, divide by 2, so it's 3. And then mid lands we're all checking here, and we check that, and that's not it. Okay. And then basically, what is it? Sorry, no, I should actually do what it does. So when we check it, it does eliminate it. But then basically our number is smaller than this. So we're going to try to go search down here, but we do that by jumping high down, right? Normally when we eliminate the top numbers, we move high down. So here is the spot we just checked. So we're going to move high down here. Okay, and now basically the code will end because high is now lower than low. Okay, so I'm going to start to show you some of the code, which goes really in depth here, but I think, visually, hopefully you can understand it and like make this chart. But I do want to mention the code because sometimes I have you interpret the code on the AP test. Okay, so here's the binary search code. And we already talked about this. We have our low, high, and I guess I should change this to mid because that's what I've been calling. All right, so mid, I just set it to a default value, and then we have something that tracks if we found it or not, because we can exit this method. This is a binary search method that takes in some numbers and a target, right? And we can exit it as soon as we find it. So we set a Boolean to false, meaning we haven't found it. So this basically says, well, we haven't found it, and low is less than or equal to high. Okay, so in that example I just did, when we didn't find it, right, this would have returned, I should have mentioned that this would return -1, the index -1, because we didn't find it, and that happened because high became lower than low. So in our code, that's the check that says as long as low is less than or equal to high, and we haven't found it, then we want to keep looping. Okay, and the loop is kind of what we talked about. Recalculate the mid, add them together, divide by 2, and then if the number at position mid is equal to our target, boom, we're done. We set found to be true, and then we say the target was found at that position. Remember, mid is an index, so I go back to our visual here. Mid is an index halfway between high and low, until we return that index here, or print that we returned it at that position. Okay, and then if the target is lower than the number we guessed, right, then we want to move high down. So visually, again, if I reset these a little bit, right, if we get a spot where this number is too big, then we say, well, we can eliminate this number and all the ones above it. So we move high, we one less than mid. And that's what's happening right here. Okay, and then if the so if neither of those things are true, then the target is greater than this. So then we move up low and make it mid plus one. Okay, and then from there, oh, I think that's it. Basically, oh, and then we return. So this method returns true or false, I guess, if we ever found it, even though it just prints it. Normally, you'd return the index, I guess. So I guess what I should have put here is this should be return -1. Because if we find it, we could just return mid here, and then if we never find it, return -1. So this code's a little bit different because it's, I guess, just returning, did we ever find the number in here? Normally you'd return where the number is found, but it's just a slight difference. All right, anyways, I got a couple more thoughts for you here just to kind of finish up, make sure we're okay. So a couple questions for you to make sure we understood this. So I want to go back to linear search once. So even though these are in order, maybe we didn't know about binary search. If we did linear search, how many comparisons would it take to find the 15? And then sort of the worst case, if it's not in the array, let's say we were searching for 44, how many times would we have to compare for linear search? Okay, so for linear search, we would just compare against this one, 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 until we hit it 15. So it would take 1, 2, 3, 4, 5, 6, 7, 8 comparisons. Okay, and then the worst case would be we'd have to compare one more time to the 22. We still wouldn't find it, right? So basically the worst case is equal to how many elements you have. So there's 9 elements here, so we'd add 9 compares, and we never found it, so that would be the worst case. Okay, so compare that now to binary search, right? So think about like how many cases would it be to find the 15, how many comparisons, and then how many would you have to find a 44 that's not in the array, and how many comparisons would be done, sort of like the worst case. Okay, so I'm going to map this out with low, mid, and high. So low will be down here at position 0. High will be up here at position, whatever that is, 0, 1, 2, 3, 4, 5, 6, 7, 8. So it would be 8. So mid would be at 4. So 0, 1, 2, 3, 4. Okay, so mid would start there. And then we check and say, okay, our target's higher than this. So we're going to jump low up here. So low is going to jump up here and become 5. So that would be one comparison. So I'm going to just make a mark. That's one comparison. Low is now 5. So we're going to recalculate mid. So it'd be 13 divided by 2, which would be 6.5, or 6. Okay, so that's going to be the new mid. So we compare another time, and we say, okay, our target's still bigger than that. So we're going to jump low up here. Low is going to jump up here. Okay, so sorry this is getting kind of messy now, but low is going to be one more than mid. So low is going to be here, which was, shoot, I lost my spot. So I think low became here, which is position 7. All right, and then we do half of that. So add them together, divide by 2. That would give us 7.5, which truncates to 7. So now we compare here and we find our target. So that's our third comparison. And we finally found what we want, so we return our position of 7. Okay, and so if we didn't find it, all right, I'll try to blast through this as quickly as I can. How many comparisons? So again, we'd have low and high, and mid would be in the 4th spot, or the 4th index, 0, 1, 2, 3, 4. Okay, so there would be mid. Our target's higher, so low would jump up here, and then mid would be recalculated to right here, right? So that would be our second comparison. We compare the 13 to 44, and we would realize that our target is bigger, so we would jump low up again, one more than mid, recalculate mid to be right there, half of those 2 indexes, all right? And then we didn't find it there, right? So we do another comparison, but we would say we have to be bigger. So then we would jump mid to one more than low. All right. Sorry, we jump low to be one more than mid. Sorry, so low would be here. Then we'd recalculate mid and they'd all fall there. We'd check one more time. We still didn't find it. And at this point, low would jump one more than mid again because we'd be eliminating everything down here. And so now finally, high would be lower than low until we'd stop. So they would take 4 comparisons. Okay, and that's kind of the long way. Like the simpler, faster way is just to take the number of elements and divide by 2. Right, so this one has, I think, 9 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, and just divide it by 2. So 4, 2, 1, and then once you finally get to 0, that's how many times, right? Because you're essentially cutting it in half by binary search. So just divide your elements by 2, and that'll tell you how many times it takes. When you hit like a harder one, like if I want to figure out how many comparisons for binary search on 10,000, just say, well, we cut it in half, right, on our first guess. So basically then we can cut that in half again on our next guess, and then the next guess after that we can cut it in half again, and then just keep cutting it in half. So I think this would be 625, and then if it doesn't divide evenly, just round it up or down. So this would be like 312, I think. Then keep cutting in half, that'd be 156. Keep dividing in half, that'd be 75 plus 378. Divide in half again, that'd be 35 plus 78, half, that'd be 39. Okay, then divide by 2 again, and you can just round up or down. So I'll just round to 20 to be simple. Cut that in half, 10, 5, 2, again, just round up or down there, 1, right? So roughly, that's how many comparisons it would take. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and if you actually want to do a quicker way, since we're dividing by 2 each time, this is actually the log base 2 function. So you could take log base 2 of whatever your number of values is, and that'll get you approximately how many comparisons it'll take. So if you do this on your calculator, I think you should get something around 13. Okay, so that's how you figure out a quick way to figure out how many comparisons with binary sort. Because it's guessing the middle, you can cut it half each time. All right, thanks for watching.